I'll just have you post those in the Slack channel for the particular day. Anytime you want, during the lecture or afterwards. And then once we get to the end, I'll answer as many of them as we can during the lecture time, and anything that I don't get to then I'll try to answer in Slack or during the office hours. So if you have any technical problems with Zoom joining, it looks like a good number of you have joined, so there's no showstopper here. Just post those also in Slack, and I'll do what I can. So this week I'll be given a little bit of a hand from my colleagues Sean Dooley, Henrik Schmidt, and Stephanie Patillo in terms of TAs. So they might be answering some of your questions on Slack as well. So please give them your attention, and thank you to all of you for that. The lectures are being recorded and will be posted online. So keep in mind that everything during this 2-hour window is recorded and will be publicly available. So during the office hours, I won't be recording those. So, it'll be a little more informal. And feel free to jump in those. I'll put those will be 1 to 3 p.m. and 7 to 9 p.m. Eastern time. And I'll put the links for those in Slack. So it's really going to be pretty free form. If you have more questions about stuff you want to ask, if you have questions on the homework, really anything. It'd be good if you could post your questions first in Slack in case we have several people with the same question. We can try to coordinate. And I'll also leave those open if you want to just join and go to your own room and collaborate with people on homework or something. It'll give you a space, sort of up to you. There's some flexibility with that. Okay, so I'm going to start recording on the second machine here now, and then we'll be ready to go. All right. Well, welcome again to anyone who's joined. Greatly appreciate the enthusiasm here. And it's pretty cool to see that we've got people from, well, pretty much literally around the world. And I especially thank those of you who are attending live from time zones that are in the middle of the night. So Goby3. It's pretty exciting to be able to put together this course over 4 days. And I really appreciate the sponsorship from Mission Systems in Australia, Blue Ocean Seismic Systems in the UK and Australia, and Raytheon Technologies in the US. It really helps mitigate the cost. It takes quite a bit of time and effort to put together a course like this. So thanks again very much to the three of you. So I'm Toby. I run a very small consulting, contracting open source software company, Goby3, as many of you know, in Cape Cod, Massachusetts, in the US. And so what is Goby? Depending on where you approach this from, it could be any number of different things. Is it a C++ library that happens to have a collection of marine robotics related code? Is there drivers for acoustic modems and what I'll call related slow links like satellites? Is it a middleware, a publish subscribe middleware framework, an open source project? More than say 2,000 species of small carnivorous fishes? Yes, Goby's all these things. The software project's the first 4. It's named after the last of those. And so, depending on how you approach this and what your needs are, Goby is all these things. And the hope is that you can come and use what you need, take that away and know more. The goal here is very much take the pieces that you need, use them and build a system. And so this week we'll be focusing on kind of maybe a holistic view of how I use Goby for kind of a lot of different parts, but keep in mind, I don't want you to lose the context that if there's only some piece of it that you want to use, by all means, and I think that the coding styles should support that. So going a little more detail there, the core library is got these modular components within it, classes for acoustic communications work, utilities for marine software, sort of general purpose utilities such as AIS, seawater calculations, empirical sound speed, density, that sort of thing. Things like NMEA 0183, very commonly used on a lot of marine sensors and things like that. And then time functionality. And also particularly supporting faster than real-time simulations, given that our vehicles move so slowly, that's usually a helpful thing. And then the other big piece of it, as I see it now, and this is kind of the three-part in Goby, is the nested comms publish subscribe middleware, which I split into kind of three main components. There's a common transport interface, which does thread-to-thread, process-to-process, and vehicle-to-vehicle comms. We'll look a lot about at that, especially tomorrow. Application support classes let us quickly write processes and applications and actually run them on the system. And then extensible marshalling schemes, supporting a variety of open source projects like protocol buffers, Mavlink, DCCL. And the design in Goby is to easily support many more marshalling schemes that you may want to use. And then I'll call it a growing list of useful applications, things you can run and use. So connections to GUIs, to GPSD, loggers. We'll look at a bunch of that code this week. We'll run that. And then various threads, mostly in the realm of I/O. So communicating with serial, UDP, TCP, CAN bus, that sort of thing. So a little background, why create Goby? And there are already middlewares, there are already open source projects out there. I think the biggest thing from my standpoint is that since marine robotics has some sort of unique technical problems, especially revolving around communications, low throughput, high latency, that's what it sort of sums down to. Harsh environments, so deployments are particularly expensive. It's going to be quite challenging to get stuff in the water, and you want to be ready to when you do. And then the sort of wide array of oceanographic sensors, many of which are specific to seawater, and also many of which have legacy interfaces. And so my hope is that Goby is kind of a beginning to some solutions. Certainly don't pretend to suggest that all this is solved. And maybe more importantly than that, it's an open source project that's building a community that we can all kind of build on it, and I think improve some of our use of software best practices along the way as a community. So you sort of somewhat see this course as giving this to you, and I really encourage those of you who are so inclined to work on pieces, build back and give back to the open source community, and that's how you build something that really reduces the reinventing of the wheel problems and stuff like that we've seen on all fields of engineering, not just ours. So quick history, the project grew out of the MIT lab that I was a graduate student and briefly a postdoc in, Henrik Schmidt's lab, the Laboratory for Autonomous Marine Sensing Systems. And it sort of started out as a handful of Moose code that then got refactored into Goby3, which was an XML version of DCCL, which we'll look at what that is later, if you're not already familiar with it. And then a rewrite of DCCL to protocol buffers happened in that sort of version 2 of Goby. And then after I graduated, I started Gobysoft, and that's sort of what's come out of that in the open source side is DCL3, which is sort of a standalone version of DCL2, and then Goby3, which is what we're going to talk about today, where the particular new stuff is the nested middleware concept. So this is kind of the syllabus for the week, is thinking about robotic systems, especially marine robotic systems, as kind of a three-point triangle of requirements and capabilities. So in a lot of cases, this triad of sensing, communication, autonomy represents trade-offs. You kind of, based on your vehicles and systems and what you want to get done, you can pull yourself one way or another and still accomplish the same goal. So if you have more communication capability, you perhaps have less need for autonomy because you can actually have humans in the loop a lot more tightly. So, a good example of that is how most of the Defense Department uses UAVs. You fly drones sort of remote control. So as you go to better autonomy, you can probably get better data from cheap sensors using techniques perhaps like adaptive sampling. Whereas if you have better sensors, if you have a really rigged out vehicle, you may need less need for outside data like communications. and you may not need as much autonomy if your sensors have better resolution and longer reach. So, thinking at these 3 points of the triangle, tomorrow we'll be talking about communications. Day 2, we'll be talking about autonomy and sensing. Communication is a bit bigger here because that's really the focus of Goby, perhaps, is on that. And you'll see that focus leach into the days on autonomy and sensing. So, more detail, the syllabus. I'll be giving a lecture today until 11 Eastern time, and then the same time the next 3 days. The one tomorrow might run a touch long. I hope it won't be much more than 5 to 10 minutes long, but anyone who has to leave at 11 hard can certainly watch the remainder in playback. And then with all these, I've got a homework assignment that you're welcome to work on. All the homework builds on each other, but I will provide my solutions at the end of each day. So if you feel like working on one assignment, you don't need to have completed the previous days fully to be able to work on the following day. So, another look at, what we're trying to do here, kind of historically, is that I see the AUV community as going from, something we've accomplished is reliable platforms. You can buy vehicles now from any number of vendors that work reliably. And we've developed kind of really nice single vehicle middlewares like Moose and Ross. And then kind of built on that, autonomy systems like Moose IVP. And platforms are now getting a lot less expensive. You can buy low-cost AUVs from a number of manufacturers now. Communications hardware is still very much a work in progress, but also still, there are a large number of reliable commercial modems out there. The throughputs are quite low still, but so this is kind of still very much in today's realm. And then kind of where we're looking is sort of supporting the ultimate goal, perhaps, of multi-vehicle autonomy, which can be useful for a lot of applications, especially when you're trying to survey large areas of the ocean. And I think that a prerequisite for that is robust multi-vehicle middleware. And that sort of blue box there is a lot of what we're going to talk about this week. And that's a lot of what Goby is trying to be. So, keep that in mind. So, I've been using the word middleware quite a bit. What do I mean by that? Sort of the view here in this graph is it's as it sort of suggests from the name, it lies in between what you're trying to really do and get autonomy and the operating system and underlying communication transports. So a core role, I think, is for asynchronous communication and typically publish subscribe architectures. So, how do you go between all these different subsystems and processes running on your computer, communicate data, and develop them in a way that's sort of extensible, flexible. And then secondary roles for middleware, there's various tools. So like launching processes, logging, health management, monitoring, that sort of thing. But at the end of the day, I don't want to lose sight of the fact that it's really the glue that holds together a system that you and I are creating to take data in from sensors, control our vehicle at some level, and then produce something useful out of it. And so, the middleware from Goby's standpoint, I'm tempted to call it a meta middleware, which I'll try to make that a little more clear in a minute. But, what do I consider composing a middleware? So this instead of a trade-offs as the last triad I showed, this is really composition. So I see it as a marshalling scheme. So how you represent your data on the wire, plus transport layer, which is, the wire itself, if you will. And here I use this a little more broadly than a traditional comms diagram would have, but this includes sort of the whole comm stack underpinning the middleware. And then applications or binaries, stuff you're actually running on the system. And the middleware can provide support for that, including configuration management, events, synchronous tasks, that sort of thing. So I'm calling this a middleware because there's really not anything in Goby that's saying you have to use a particular marshalling scheme or particular transport or particular applications. So bring your own. Given that, I do have what I call reference implementation for it, and that's what we're going to be playing with a lot that makes heavy use of Google protocol buffers and GCCL, 0MQ, shared pointers, and acoustic modems, and satellite comms for the various layers of transport. And then we'll look at a handful of applications, and you'll write some of your own as well. So a little quick look at my view of existing middleware and AUVs. It's largely Moose and Ross to the degree that it's open source. So Moose, a good number of you are familiar with, especially because of the IVP project. It's got a TCP transport for process comms. Marshalling scheme is a CMOOS message, a thin wrapper around string double or binary, as application support using a CMOOS app. Now, ROS is really widely used and starting to become more widely used in the marine community. Similar concept, TCP with central broker for transport, and some amount of shared pointer interface comms. And then its marshalling scheme is a little richer. ROS message where you define your own structs, compile them into classes. And there's a loose specification for application support in the form of a ROS node. I put LCM on here too. This hasn't really seen that much use in the marine world, but it's a really nice counterpoint to the other two because it's got a different design for the transport layer. Is a UDP multicast. So there's no need for a central broker, which is kind of cool. Though you do need to deal with application acknowledgements, which isn't as nice in some cases. And marshalling is similar in concept to ROS message, so LCM type. And one thing I want to note is none of these are specifically designed for marine vehicles. I mean, Moose was, that then it quickly sort of moved away to different domain when Paul Newman went to Oxford. And so the other thing is that they all kind of provide the whole solution. They mandate a specific transport marshalling scheme, so it's a little harder to decouple if you have a system that you want to bring your own transport or bring your own marshalling scheme based on what you're already using, or technology changes as well. So the innovations in Goby really revolve around this nested communications, which I keep alluding to, and we'll get more to in a second. But basically, the communication approach varies depending on what your actual characteristic throughput and latency scales are. So you do a different approach for thread to thread as you do from vehicle to vehicle. And it's also neutral about this choice of transport marshalling scheme. So you can more easily include external innovations with regards to networking and data presentation. I think, it's also nice that you can have newer project-specific marshalling languages without having to modify the underlying middleware. And then the other piece I'm trying to bring to this, which is still a work in progress, but we'll look at as regards to Moose today and tomorrow, and especially Wednesday, is interoperability with existing middleware, because there are very few systems now that want to come from totally scratch. So what do I mean by nested communications? I think the core idea here is that, especially in the marine community, the networking approaches, the physical layer and shortly above that, are fundamentally different based on your characteristic latency throughput scales. So non-marine systems arguably interprocess comms between vehicles and within a vehicle are really on the same scale of throughput and latency. I mean, your Wi-Fi links are going to be slower than an internal Ethernet, but they're not an entirely different scale like we have with acoustic comms. And marine systems, interprocess comms are really an entirely different scale. And the reason for this is physical, acoustic communications limitations, and the fact that we have to use acoustics in water because the propagation length of light is very low, as well as the way we deploy vehicles. So sparse deployments. So you may have vehicles spread across the globe that need to communicate, and so you're using things like satellites that provide you with low throughput and relatively high latency as well. So what does that look like? On an order of magnitude scale of throughput, it's bits per second here. So this is a logarithmic scale. You're looking at inside of a process, thread-to-thread comms is extremely fast. How fast you can just move a shared pointer around. And in between processes, if you have like gigabit Ethernet, incredibly fast. And then this is a huge drop. Now you're going to acoustic comms or something like satellite comms as well. So you have this massive drop down to say hundreds of bits per second. And then there's a sort of fourth layer. You can conceive of building a system around that where you might have acoustic comms, then satellite comms to communicate between isolated squadrons of vehicles. We'll mostly focus on these three on the left this week: interthread, interprocess, intervehicle. So looking at this in a different concept, so I call this a nested communication scheme, and this is sort of how you see it's nested in sort of layers of an onion. So each conceptual layer here is going to require a different transport and marshalling scheme to approach it. And so again, you have interthread kind of in the middle, processes around that, vehicle to vehicle outside of that, and you can build more if you wanted to. And what Goby brings to this is, how to do this essentially, and providing a common interface in the C++ code for the publish subscribe, and then cross-layer forwarding. So how you get data out of one layer and into the other. And so drilling down a bit more deeply into how this is implemented, Goby has this idea of transporter classes. And these transporters, as they're so called, are in two categories, or concepts, because there are going to be multiple implementations of each concept. So there's the portal concept, which connects one nested layer to the other. So from interprocess to interthread, for example. And there will be exactly one portal per node per layer. So on the interthread layer, the node is thread. Interprocess layer, the node is a process. And the intervehicle layer, the node is a vehicle. And if you went to the intersquadron layer, the node would be a squadron or collection of vehicles. And then the other type of transporter is forwarder. And that forwards data from any of the interlayer nodes to the layer's portals. So any of the other nodes you have hanging out within that layer is going to use a forwarder. And so you can have any number of those per node. So you have potentially any number of intervehicle forwarders on a given vehicle, so that different processes can communicate externally to other vehicles without having to actually be connected physically to the modem. And so, for example, the interprocess portal would connect the threads within a process to the rest of the processes. So you could have secondary, tertiary threads communicating data, and then they get sent out through that portal to the other processes. And this will become more clear when we actually start looking at code, especially tomorrow and the next day. And then the forwarders, as I said, would run on those other threads and pass it out. So pictorially, what does this look like? So in this very simple scenario, well, it's simple as I can to make it the point. We have a vehicle one and a vehicle two. Within vehicle one has two processes, process one, process two. And vehicle two just has one process, which I'll call process three. And so the blue line and the red line indicate two possible publication and subscription paths. So in the case of blue, we have a publication here on thread one of process one of vehicle one, and we have a subscription for it over here on vehicle two of process three. So how this message actually gets from this thread on this process on this vehicle is it basically gets forwarded down to the innermost layer that's supported within that particular node and that layer. So in this case, you have an intervehicle forwarder, forwards it into the interprocess forwarder, which forwards it into the interthread transporter, which is then shared between all the threads on this process. So that then gets sent out to the one that's the portal. So the portal takes it and then sends it over to the portal for the intervehicle layer over here on this process, which then actually sends it out, say the acoustic modem, over to the second vehicle. And so this path is you don't need to know this necessarily to use it. You just call publish on over here and it shows up over here, but this is how it's implemented. And then the red line is there's two possible subscriptions. One subscription is vehicle one, process one, thread two. So over here. And then the other is on process two of vehicle one. So this one doesn't ever leave the vehicle one. So it's published over here. It's published over here on this process, gets sent into the interthread layer, which then gets sent over here because this one's subscribed to it. It gets sent over here because this one's got the interprocess portal, which is how it's going to get over to process two. And I think this will become a lot easier to get your mind around when you start doing it, and that'll be tomorrow. So, bear with me for now. So that's the sort of conceptual design of Goby3, and that's sort of the meta middleware part of it. And then we'll, now we're gonna actually get to writing some code, doing some code. We need an implementation. And so the implementation that's provided in the open source version uses on the interthread layer is just the standard C++ shared pointer, which means we can support all different types of code, and you're not really actually, it's a bit of a sleight of hand, but it's a useful one. You're just passing around shared pointers in a publish subscribe manner. At the interprocess layer, I'm using the ZeroMQ project, which, if you're not familiar with, is sort of a lightweight extension of sockets to a publish subscribe, as well as a couple other models. And then for marshalling schemes, using Google protocol buffers and DCCL primarily. Though it's pretty easily extensible to any serializable type. You might want to use, JSON or Captain Proto or a number of other new things that are coming out. And then in the intervehicle layer, we have what's really kind of Goby2, the Goby ACOM stuff, and DCCL, which is also my project. And that's also could be extended if there's work that makes sense to put in there, which we're just starting to see, I think. And the whole implementation is fully event-driven, based around the standard condition variables in C++11. So, marshalling, another one I haven't really dug into. What do I mean by that? The Wikipedia sentence describes it really nicely. It's just the process of transferring the memory representation of an object to a data format suitable for storage or transmission. And more concretely in C++, that looks something like, I've got a struct or class. I want a bunch of bytes that represent it. So I can send that over some kind of wire. And then I want to take that back, parse it back into a structure class. And so many of these marshalling schemes also support different programming languages, quite a long list in the case of the protocol buffers. And so example projects including protocol buffers, Mavlink, which is often used for UAVs, DCCL, JSON, message pack, ASN1 being an old one. And what we'll call these in Goby is marshalling schemes, or just schemes for short, since it's kind of a mouthful. So if you see schemes running around, that's what it refers to. So then, looking at the transport layers, we're going to kind of work our way out from the onion here, on the bottom here. So the inter-thread reference implementation is based around standard shared pointer. So that basically means there's no constraints on what message types you can use. As long as you can represent it in C++, you can use it. And so the publisher in this case basically takes a shared pointer, publishes it, and the subscriber gets that pointer. And as I said, it's a bit of sleight of hand because you're not actually marshalling anything, but it's really nice because it allows people who are either unfamiliar with thread memory management or who want to just use the same publish subscribe paradigm that you used to, say, on interprocess code, to write multi-threaded code. And the other nice thing about it is by using the same APIs, you can take code that you wrote process to process and then port it fairly easily into thread-to-thread comms. So, you can, if you decide you built something that works pretty well, but you need faster communication or higher throughput, you can pretty quickly port that over. So then the next layer out is the interprocess layer. And the reference implementation for this, as I mentioned, is based off of 0MQ, which is a separate open source project. It's quite nice. And currently it support DCCL protocol buffers and Mavlink, but it's trivial, extensible, any serializable type. So you can take your own marshalling scheme, implement a couple of functions, and use it in Goby. And so within this reference implementation, there is a broker called the Goby3 from Goby daemon, which handles the multiple publishers, multiple subscribers with 0MQ. And the other nice thing about 0MQ implementation is that you have the subscription forwarding. So if you're publishing data that no one's actually using, that won't go anywhere. And we'll look at that a bit more on intervehicle. And then the last thing I should mention, those of you used to Moose and Ross, this is the analysis layer for what Goby is providing. So process-to-process comms within a fairly fast transport layer, Ethernet, or inside a local host as well. So intervehicle is kind of, this is the most interesting, I suppose, for us probably. And so we'll spend a fair amount of time on this. There's the implementation in Goby of this modem driver, which is a common interface for, we can write drivers for a whole bunch of different devices. So like specific modems, like micromodem, Methos modem, or satellite links, Iridium, that sort of thing. And then for the marshalling languages, we have DCCL, which I'm calling it a static unit safe lossless marshalling language, which is a mouthful. But basically that means that you have physical bounds for each of your fields, and it also has arbitrary size fields. So you can have a field like temperature that you state goes from 0 to 40 degrees Celsius. And DCCL will turn that field into a 6-bit integer in that case. So it's very compact and has unit safety, which is pretty nice. So the third piece is this dynamic buffer, which is a deadline sensitive priority queuing. And we'll look at that in the homework quite a bit more, but basically you have a bunch of different types of messages. You can assign a priority value to them, but you can also assign a deadline or a time that they will expire. And the messages that are chosen to be sent are a mix of overall priority as well as the deadline. And then the last thing is a subscription forwarding implementation also on this layer, which is even more important than it is on the interprocess layer, because you don't want to be sending data over your acoustic modem that no one actually wants. So those are the 3 layers that we're going to look at, and those are the 3 that are in the open source implementation. And switch gears a little bit here now to a couple other things that are in Goby that are useful. One of which is the design of the project is really heavily focused on what can you do with the compiler with static analysis. And there's a lot of emphasis on not only sort of standard type safety and things like that, you can actually do what I'll call deployment safety, for lack of a better term, but basically understanding your structure of your publish subscribe architecture at compile time. And so based on the way that the groups in Goby, which are analogous to ROS topics or LCM channels or Moose variables, if you come from any of those backgrounds, the groups are declared at compile time. At least that's the preference. They can be declared at runtime as well, but preference is they're declared at compile time. So you can then generate static publish subscribe graphs, like this little example down here where I've got one publisher and one subscriber publishing a couple of different messages to each other. And then there's also what's sort of on the horizon is this necessity parameter where I say in my system, I need to have this publication, GPS control, but I currently don't. So it draws me a red line. And the next step beyond that is having it actually tell me I need this, and maybe have some notion of what would provide it if you give it a library of different applications. And this is novel amongst the existing middlewares. And you look into this a bit too more this week during the homework. So I'm going to quickly show a performance slide, not so much because I'm really trying to say that Goby is actually faster than the other middlewares, because it isn't necessarily. In fact, it's a little bit slower in a few cases, but that its performance is comparable. And so you're not losing anything by switching to something that's flexible enough. But now an inter-thread layer performance is fairly similar to the ROS nodes, nodelets, I believe is what they're called. And then inter-process is spread around here. 0MQ is why this is faster. 0MQ is pretty efficient, so it's actually faster than on the. Not trying to claim any credit for this really. That's 0MQ is doing. And then an inter-vehicle, there's really no analogy in these other middlewares, so it's obviously much higher throughput. So this is the latency between publisher and subscriber. So much higher latency, but that's the underlying transport link. So the third part of this, so I talked about the marshalling schemes briefly. I talked about the 3 layers of the transports. The third piece of that triad of the sort of what I consider Goby3 to be composed of as a middleware is application support. And that'll be a good chunk of the sort of second half of this lecture after the break, is looking at the application support code and building that up so you can use it. And the single thread application is inspired kind of by CMOOS app, but I'll say with sort of significant improvements. We had configuration, command line parsing, which is nice. That saves a lot of work. There's a single virtual method called loop, which if those of you who use Moose is sort of analogous of iterate, that you can use or not, depending on what your application needs. And then there are no other virtual classes than that, or virtual methods rather. And the constructor handles the equivalent in Moose of the on startup on connect to server. And so though, what this provides you is it contains an inter-process portal, so you and an inter-vehicle forwarder actually, so you can do publish, subscribe between other processes and between vehicles with this. Given the name single thread, there's no point to have an inter-thread portal transporter inside of this. So the other one, so quickly, as we'll look at this in quite a bit more depth at the end of today's lecture, you're not talking about writing a whole lot of code to have a basic publisher subscriber. So basically, at a minimum, you've got a publisher over here that's setting up publication and publishing it, and then over here, subscriber, the message that they're using, a group to send it over, and a configuration message over here. So this is a complete 2-process publish subscribe code. Like there's nothing I'm hiding here, and at the end of the lecture, we'll actually build up the bones of one of these. So I don't want to belabor this now, but it's mostly a sort of sense that at a minimum, you can have a publisher or subscriber on a screen full of code. The second application support of the two in Goby is the multi-thread application, and so this is really very similar to the single thread application class in its API, except that it also has thread-to-thread support. So you can spawn threads with it, and you can join threads with it. And each of these threads that it supports is a class of its own. And by making each thread a class, you avoid pretty easily any accidental memory contention, because if you just keep all your data at the class level and don't use any global variables, which would be generally good style as well. So you don't have any issue as long as you're just publishing, subscribing between the threads to pass data, and you keep all the thread at a class scope, then you're good. And then the other piece of that, besides having these subclass threads, is that they can be spawned and joined as necessary by the kind of parent application. So before we dig into the applications a little bit more, I wanted to give you guys an overall view of the repository structure of Goby. So just give me a second here to bring up this second. This. So you're not going to really need to dig a ton into the code of Goby3 itself for this project, but I do hope that a good number of you will choose to sort of help work on the project at some point in time. So I think it's nice to get an overview of where the actual repository structure. So each one of these bubbles is a folder within the Goby3 project. So the root is Goby3 or whatever you cloned it as from Git. There's a little bit of support code for CMake for building it and some scripts. Then there's a folder over here where the default build creates, which is a mirror of the of like USR for binaries, libraries, include headers and other miscellaneous share stuff. And then the main, most of everything is in SRC. So that's the source code, which branches off of that. And the core library, which is libgoby.so, gets built out of a good chunk of that code, of which there are 4 what I'll call modules, because they're all built into one library. There's the ACOMS module, which handles kind of the underpinning implementation for the inter-vehicle code. So the dynamic buffering, modem driver, medium access control based on TDMA. Then there's this middleware folder and subfolders that support all the middleware related stuff, transport, marshaling, application support. And there's some time function stuff. And there's utility libraries, which include the stuff that's like marine specific utilities like AIS messaging, or seawater functions. Line-based comms has the stuff for like NMEA 183. And then outside of that core library, there's a couple of additional libraries that are built. So there's this libgoby Moose, which supports all the Moose interfacing related code. Libgoby 0MQ, which supports the 0MQ implementation of the interprocess comms. And these are built separately because they're optional. If you don't have the dependency and you don't need them, you don't need to build these libraries. And then the last core piece is the application source codes. So under source apps, there are a number of different, ultimately binaries, and it's the little square box. This is something you can actually just run. There's a variety of things that support the core underlying middleware, which is like tools related to log parsing, the static analysis tool, the Goby Clang tool. And then there's some Moose applications that some of you may have been familiar with, like PACOMS handler, and that's still supported, which implements the sort of Moose side of the ACOMS stack. And then the 0MQ stuff, which is all of these processes that you can run on the base implementation, which I'll run through all of these shortly on the slides, so I don't belabor them now, but these are applications that are useful for a variety of different tasks. So, I distribute this slide so if any of you want to kind of get what the roadmap, or if you're trying to sort of browse your way through the Goby repository, you won't be totally lost on an initial go. So I'm kind of going to do a little view through all the binaries that are included within Goby or applications. The first of which I'll mention is the logger. So there is a very simple logger intentionally because I don't want to enforce a particular set of hardware or operational scheme on the people. So it's it writes a flat binary file that's almost just the messages on the wire. It just wrapped with a prefix and a checksum to allow you to actually read the rest of the file if there is, for some reason, corruption within it. And then everything that's kind of done with it is done with this plugin API, which allows you to both store additional metadata. In the case of protocol buffers, there's these descriptors that allow you to read messages after the fact without the original proto file. And then in post-processing, there's Goby log tool that allows you to convert, at the moment, DCL protobufs to HDF5, which is a scientific data format, and text for debugging. And HDF5 can be read directly by tools like MATLAB or Python, as well as a whole slew of programming languages that support it. So that's kind of the main data product that I'm using out of this. But during runtime, the mode is very simple. Write it as binary straight to the file because it requires the fewest constraints on what the user's got for file system and CPU load and things like that. The next thing we'll look at is this Goby3 is the inter-process broker for the 0MQ implementation. And this is composed of, for those of you who are kind of interested in the guts from a 0MQ standpoint, there's really two main components. There's what 0MQ calls a rep for reply socket, and that accepts the connections from various clients. And clients basically say, I want to start publishing, give me a pair of ports. And this pair of ports is dynamically assigned for the system and passed over to the clients. And then this router is the other main piece of Goby3, which is a 0MQ xpub xsub, which is a multiple publisher to multiple subscriber, basically, proxy. And that allows us to have multiple publishers of the same data type, multiple subscribers of the same data type. And the third piece in Goby3, this isn't strictly necessary, perhaps, but it's a good place to put it. Every layer needs a portal. And since any system running with this 0MQ inter-process implementation is going to be running Goby3, it's a good place to put the inter-vehicle portal. So you don't have to run a separate process to have it. And so this is what connects to the actual modems and passes data out from any forwarders running on the system. So you'll make use of this a good deal in the homework this week. So then continuing down the kind of laundry list of applications that are in Goby that can be useful, there's two viewer interfaces. Not viewers themselves could connect to other projects that are either open source in the case of OpenCPN. So OpenCPN is a chart plotter. You can load electronic navigation charts on it, and you can put in your own ship data and a variety of other useful things. And what the Goby interface does is it provides your vehicle positions as a fake AIS message. And thus you can use OpenCPN without modification. You're limited, though, by what AIS can support, which doesn't include things like depth. So I find this interface particularly useful for unmanned surface vehicles. The other one is the Google Earth interface, or Jove as I call it, which is this other project that I have that is a blend of MySQL, PHP, and Google Earth. And the Google Earth interface, basically, you open Google Earth and then it queries this server for KML, which is their XML-based updates for position and whatever, trails and things like that. And the nice thing about this one is, even though Google Earth isn't open source, it is free, and it provides visual depth information. So so visually you can see where your vehicles are. So it's often a mix of these two that I'll use this week. And take what you will, I guess, depending on what your needs are. You can use one or the other or neither. So the third sort of user interface thing is the Goby Liaison, which is a web browser-based interface. And this one's built around a C++ web toolkit project called WT. And there are two, so you can build your own tabs around WT. There are two built-in ones that come with Goby, which is the first is the scope, which allows you to see all the messages that are being sent over the interprocess layer for a particular vehicle. The other is Commander, which is essentially you have a message in protocol buffers that you want to be able to send by filling it out and clicking send. So commands typically, but you can use it for other types of debugging. Anytime you want to kind of poke the system with a message, that's what this provides. So between the two of those, you have viewers that you can see the vehicles, and you've got command and some amount of low-level debugging implementations. And you can envision a number of additional extensions to this tool that I would like to add over time, but the sort of core functionality gets you going. The next tool on our list, kind of working our way down here, is Goby front seat interface. And we'll talk about this one quite a bit on Wednesday. But brief overview right now is the implementation that I'm doing for control on Goby is typically that which I've taken from Moose IVP, which is this backseat front seat abstraction, where you have a backseat computer which runs the payload autonomy, providing some amount of desired set points, often heading speed depth, and then a front seat computer which is running the actual control system and then providing control surface outputs. And that abstraction is nice because it separates the design of the control algorithm for the vehicle based on the vehicle's design from the autonomy system, which generally doesn't care a whole lot about the specifics of the underpinning control system. And so what this in Goby does, this interface is extensible by, you can create a plugin, essentially write a driver that implements the interface to your front seat computer, and then you can use the existing sort of backseat half, if you will, of the process without modification. And there are 4 plugins that come with the open source project. There is a basic simulator one that we'll be using this week for all of our work. There's one for the General Dynamics Bluefin vehicles, one for the wave gliders, the SV2 version of wave gliders, and one for Ocean Server Ivor, the Ivor 3. I think it should support the Ivor 4s as well. So that's and I encourage any of you who have other vehicles and want to use this, please write a driver and contribute it. And I'm happy to work with you to figure out how you can do that if you want. So then, kind of randomly picking around with these binaries, we've got this GPS, Goby GPS, which I'll call in beta because I haven't actually deployed this yet. This one Sean wrote, and connects to GPSD, which a lot of you are probably familiar with, which is a Linux project that provides a daemon for GPS receivers. You can plug in any number of GPSs over serial or Ethernet, and then GPSD aggregates them and serves the data. And so Goby GPS is essentially a client for GPSD, connects, grabs the data from GPSD, and then republishes it all on Goby3 interprocess so that any downstream applications written in Goby have access to the data. And you can filter out the publications if you want, based on if you have like 3 GPSs and you only want to listen to one, you can do that. Then there's Goby Corner application. So what this does is it keeps track of whether the applications on your system are running or not at a minimum, and if they're implemented to do so, they can provide more detail about their health. So at a minimum, Goby Corner, give it a list of applications. It keeps track of whether they're all still connected, reporting back to this. So on a regular interval, it asks every application that's on its checklist for a request for health information. It goes to the application, which responds with, yeah, I'm still running, things are great or not. And then with all the responses or lack of responses, it creates a report saying, yeah, everything's up and running, the system's good, or the system's degraded because one of these applications reported that it's degraded. Then along the same lines, sort of, there's this Goby terminate tool, which is, okay, now I actually want to bring down the system, but I'd prefer not to just sig term everything. So Goby terminate can be used to say, ask an application to quit, and the application, if things are working fine, says yep and quits. And if there's no response after some period of time, Goby terminate itself exits with a error code and then you can use that to feed either a systemd or your own script with a sigint, or follow up even with a sig kill if it gets really bad. So design, and this is what's used by Goby launch, which we'll get to in a bit, which we'll use this week. Goby launch. So the last thing here is a script. It's a bash script that is really a convenience for simulating. And so you can write kind of a list of processes you want to run with their command line parameters. And Goby launch will launch them all in their own screen session, so you can attach and detach to them at ease. And then when you control C the Goby launch, it will send a clean Goby terminate message essentially to all of them. If that fails, it'll sig into process, and if that fails, which it really shouldn't, it can, sig kill. And so, at its simplest, the Goby launch file is essentially a script that uses Goby launch as the interpreter, and then you just write the list of processes that you want to run. All right, so that kind of that hits sort of everything that's in the core of Goby. And I'll look now at interoperating Goby with other middlewares briefly. We'll look more at this on Wednesday when we deal with the autonomy stuff, because a lot of the autonomy work will be using Moose IVP. But my goal here for interoperability with other middlewares is to essentially create these gateway applications, of which Goby Moose Gateway exists. And with this gateway application, this knows how to connect to both sides of your sort of binary star, the Goby3 interprocess, as well as, in this case, Moose DB. And then users, that can be the Goby project provides some, you can provide your own plugins that convert messages as needed between the systems. And since these plugins are written in C++, it could be as easy or as complicated as you need them to be. So for this simple example, I want to go from two Moose variables, test latitude and longitude, into a protobuf message that will be used on Goby, and then the inverse, turn it back into two different Moose variables. And so, that looks like in code. The point is, here is a plugin, it's very short, and I want to go from the Goby to Moose. I subscribe to this protobuf message, and then I call the two Moose, notify as the publication call in Moose. And then similarly, on the other side, it's a little more complicated because of the way Moose is designed, like to split everything out in all these different variables and keys. I have to aggregate two messages, that's test latitude and longitude, and so you can buffer one message and trigger off the other. So when I get a message of the trigger type, it calls this callback, and then I can take both of them out of the buffer, make my single message, and call publish on it. And if you needed to do a lot, you could do all kinds of stuff in here if you needed to convert between unit systems and whatever. So the design is, because they're C++ plugins rather than some kind of other interface language that I could come up with, like an XML definition or something, that you can do whatever you need to, but you have that flexibility. And as I mentioned, or at least put up here, I'm going to try to do the Goby to ROS translation a similar way. You'll have essentially this Goby ROS gateway that connects to the ROS master, and then also to the Goby3 interprocess side, and passes messages based on whatever topics you need to subscribe to and publish. Okay, so it's been almost an hour. I want to give everyone a 5-minute break for anything you want. During the break, if you have questions, comments, feedback on anything, let me know in the Slack channel. And with that, we'll start again at 10. So feel free to take a break or not, as you will. All right. Hopefully everyone's back, filtering the way back in here. Got a fair bit more to go through, so we'll get going again. All right, so after all that kind of high-level stuff, let's take a quick break and look at something a little more fun. So this week during both the remaining lectures and the homeworks, we'll be focusing on a particular deployment in simulation. And this is going to be a fleet of up to 10 autonomous underwater vehicles trailing an unmanned surface vehicle, or USV. And this USV will be following a pre-planned route initially. We'll have a topside, which represents either a ship or some kind of shore station communicating to the USV. And then for communications, we're going to simulate acoustic communications from the AUV to the USV since they're underwater. And then from the USV to topside, essentially have simulated satellite comms. And sort of to give you guys a little bit of a taste of what this looks like, I've got two different views here of this simulation running. So this view on the left in P Marine Viewer is kind of the inside view, or maybe what I'll call the simulator cheaters view, which is the one where you can see in real time where all the vehicles are. So you got this little USV shown in green, which is being trailed by this fleet of 10 AUVs. And I should note this is being run at 10 times real speed, which is why things are moving so fast. So we use a sped up simulated clock to make this faster. And so then down here in Google Earth, this is the Jove interface that I mentioned earlier. This is the view from the topside operator. So you have the USV where you get pretty regular updates, but then the AUVs are on this slower TDMA cycle. So you end up getting an update from, say, vehicle 3, vehicle 4, vehicle 5, vehicle 6. And these times are you have to multiply them by 10 to get the real delays because of the warp 10. So you can see it looks like is different, visually a different effect, but where the vehicles actually are is in this arc. We just haven't heard from some of them for a couple of minutes. So I'm not going to, we're not going to do a whole lot more of this now because this is what we're going to spend the week playing with. But I figured it might be kind of fun to look at something after screens of technical text. And so today's homework is going to be to get this running for yourself. Download the virtual machine that I provided and get this running around for you successfully. And then the homeworks for the remaining days will be adding pieces, changing pieces, working with this in a variety of different ways. So put the simulation aside for now. So before we get to that trail example, we do have a simple alpha example that I'll have you look at, which is especially nice for those of you who have used Moose IVP. It's the same mission that comes with Moose IVP, but adding the components in from Goby. So the Goby front seat interface, which is what connects the payload again with the front seat or control computer. And we'll be using it with the simulation plugin. What I want to emphasize is that what we're doing here can be, in some sense, pretty quickly swapped for using a real vehicle or a real vehicle simulator. And by that, I mean a simulator provided by a manufacturer, like the ones that Bluefin and Ocean Server provide and stuff. So you can, the whole thing we're trying to do here at Goby is to build as close to a real system as we can, simulate it, and then when we go in the field, it's trying to pull out only those pieces that actually matter, that differ, and put then the real thing. Because otherwise you're simulating something that isn't meaningful if you're not running nearly all the code. The other piece that's in this that isn't in this Moose IVP alpha mission is this USV manager, which is what's publishing the data over the inter-vehicle link to the top side. And then the final thing is Goby3 to actually connect together the inter-process comms, as well as connect it to this, both of the comms links we're going to simulate using UDP multicast messages, but with medium access control and packet sizes that are representative of what you'd see in an actual satellite link or an acoustic comms link. And then the other piece is the top side. So you have visually the Google Earth interface as well as OpenCPN. And then the Goby course Goby3 course topside manager is the sort of analogy of the USB manager. It subscribes to the position data and that. So you'll run this one first, look at it first, and then you'll run the full trail example and look at that. And that's the sort of progression that will hopefully build up a little more cleanly. So launching this, you know, when you go to launch this, there's a, which I haven't really mentioned yet, there's a Goby3 course project folder. There's the Git repository, Goby3 course, that has everything in it that you'll need for this course. It has the source code that's related, launch files. It also contains copies of all the lectures, so the slides and any lecture notes that I have in subsequent days. And so within this project, there's a launch folder that contains the scripts that you need to, and configuration you need to launch this. So essentially, you'll launch the vehicle, you launch the top side, and then you can open the viewers. And I've created a separate little video to save time in this lecture that goes through this whole process, and it's in the homework OneNote. So if you want a lot more kind of hands-on with getting that set up and launching, you can watch that video. It's about half an hour in total that goes through this. But you know, so when you're done launching this, you just Control-C the two applications, and you're ready to go again. So another piece that we should mention, because it gets used a lot in the code, is Goby's debug logger, and it's glog for Goby logger, and it acts much like standard cout. And so the debug logger is distinct from Goby logger that writes a log file of your mission data, in the sense that it's intended really mostly for debugging, providing a separate log file for each application potentially that is configurable in what it actually writes, depending on whether you think you're going to be really needing to debug or not. So it has this runtime configurable verbosity settings that you can set all from warn, which is like the most important warnings, all the way down to debug 3, which is the very nitty-gritty debug stuff that you almost never want to see. And a lot of the underlying Goby3 implementation writes the debug 3. So if you turn that on, you'll get a lot of stuff. Goby logger also adds thread safety, so each log message will be discretely, it'll be like atomically written before the next one is, which you don't have to worry about. It just, you know that it exists. The other thing it can do is it can write to both a terminal and potentially debug log files simultaneously, which can be handy because sometimes you want to have it in the terminal window when you're like working actively with the simulation, or you might want to write it to files for later analysis if you need to run a debugging output on a vehicle. And the final thing is the support for colors and grouping of streams. So you can have different conceptual streams of data from a given process that then can be displayed in separate groups in this ncurses-based user interface, which we'll look at as well. So simple, you know, what it looks like syntactically. There's this function called is whatever the verbosity setting you want the remaining sentence to be. And how this actually works is is returns true if you're logging at that level or higher. So like is verbose would be true if I'm logging at verbose debug 1, debug 2, or debug 3. And if it's true, then it has to evaluate the second half of this, which is the actual message. If it's false, the program just continues right on. So the only cost to having these in your system when you're not using them is a single Boolean check. It's extremely fast. You don't have to, you're not assembling the entire stream if you're not actually writing it anywhere. So you can develop the code, use the debug sentences, leave them in there, and then just turn off the output, and the runtime overhead is minimal. The other thing that the applications do is parse configuration for you, configuration parameters as well as files. And this is done through a concept called a configurator in Goby. And the default configurator and the one that you'll be using is using protobuf. So you use protobuf not only for messages between the processes, but also as a message that defines the valid configuration parameters that your application can accept. And then you define this message, you load it in, and the rest of the parsing is done automatically by this underlying protobuf configurator. And I should mention that for when you're running the alpha mission, the configurations that they're reading are in these subfolders, topside config and USB config. And the homework will guide you through that a bit. So within the configuration, every Goby application is going to have a common app block. And this can be sort of as much or as little as you need to have. And what can be put in this app block is what you actually want to run in terms of verbosity for the debug logger, glog. So in this case, this says I want to write the glog output to this directory using the debug2 verbosity. So quite a lot of information. The simulation settings, when you're running faster than real time, it is going to be a warp factor of 10 in this case. It is going to say I want to run the clock, the real clock, if you will, at 10 times the actual real clock. And so warp factor of 1 would be real time. And there's also a little bit of support for basic UTM projection geodetic conversions, and that's also configured in here. That's just not shown. Then almost all of your applications are also going to have an interprocess block, because that's how we configure which Goby3 they communicate to and how. And at the simplest, it can be empty and it uses the default Goby platform. But as soon as you want to run more than one vehicle on a single computer, which we'll be doing in all of our demos this week, you need to define either the platform name, which creates a socket for when you're doing comms inside of one computer, uses a Unix sockets implementation, or if you wanted to do interprocess comms across a couple of networked computers inside of a single vehicle, you could use the TCP transport, run Goby3 on one of your processes and have the others connect in over TCP. So those are the two options. And there's also, which is not shown, you can configure 0MQs parameters like queue size and the worker thread count within here too. But nearly all the time, those can be left at the defaults and they'll work fine. So the last thing on the slides I have is how to sort of think a little bit about the debugging, and the notes on the homework will also look at this. But so when you're running 12 vehicles or 11 vehicles on a topside, which I was just running, that's a lot of applications. So there's potentially a lot of debug information that you may or may not want to see. So one of the things I'm going to get proficient with is how to turn on and off various debugging settings in Goby, so that you can, if you think you might need to look at the output of something and debug it, you can turn that on without necessarily turning on huge amounts of debugging information for every process running on your computer, because you'll bog your CPU down and you'll write gigabytes of disk space, and we don't want that. So Goby launch by default sends every application's terminal output into this tool called GNU Screen. And what screen is kind of like a terminal window that's hidden to you. And you can attach and detach to it with a real terminal window as you want. So if you do like screen-ls for list all the screens, it'll show you all the screens that are running on your system in the background. And if you want to look at the output of a particular process, like for example, the USV's Goby3, you would reattach it with a -R, and then it would show up in your current terminal window as if you run that right in that terminal. And if you're done looking at what you need to see and you want to leave it running, you can detach the screen, put it back in the background basically with the Control A and D. So these are kind of the core commands that I use all the time with screen. You can also look into their help manual, and there's a lot more you can do. The other big thing on debugging to remember is that Goby applications default to quiet. So if you don't give it any parameters related to verbosity settings, it will put nothing out. So it can be a common sort of misstep for new writers is to put in all these glog messages and then you don't see anything. So in order to actually see debug output, you need to provide either the -V for various verbosity settings on the command line. So like single V, double V, triple V is increasingly verbose. And that corresponds to, in the launch file or the config file, the verbosity setting of verbose debug 1, 2, 3, and so on and so forth. Then there's also the final optional piece. You can add this ncurses GUI, which shows the same level of data. So you pick whatever verbosity you want, like debug 2. And if you add ncurses as well, it'll split it into these separate windows that will show you the different streams of debug data in different windows. And I'll let you play with this during the various homeworks. So the rest of the presentation today, we're going to switch gears a bit over to how I'm going to present. The rest of this week is going to be largely not slides, but with code. And so what we're going to do here is look at how to build the basic application from scratch, because I really don't like giving people magic code and telling them, copy this everywhere and it'll do what you want it to. So there's a little bit of jumping ahead in the sense that you're not going to actually use this today's homework, but you will need it for tomorrow and tomorrow's homework and the rest of the week. And it also gives us a chance to look at the various tools that I'm going to be using for the rest of the week's presentations. So let me get this up onto this workspace, and let me actually open a bit of code because I want to get your sense here before we get going. So I've got some code, I've got terminal window and size here, and what I'm going to ask you all is this readable? Because I can make everything bigger or smaller, and you can also zoom your zoom, which I realize is a bit of a confusing terminology. But within the zoom settings for the meeting, you can choose the size of the screen and show it at higher percentage. So if there's only a small number of us that find it too small, I'm just going to ask you to zoom your own zoom because there's only so much screen real estate we have here. And we'll go with that. All right, so yeah, about most people have voted here. So for the rest of you could just weigh in if you don't mind, and we'll close this. All right, so everyone thinks is about right. A couple people a little small. So if you think it's a little small, I'll just ask you to use the zoom settings to increase your window size, and we'll go with that. The other thing I should mention is that the whiteboard here that I'm using in HackMD, you're welcome to join that. And I see like 9 of you have already done so separately. And so you'll see that synchronized separately from the Zoom display. And that might be useful depending on what screen real estate you've got, because I'll be switching between showing that and maximizing the code window and things like that. So I won't always be able to have the whiteboard open, whereas if you have it open on a second computer, you can. So that might be helpful, and that. So since it seems pretty good on the size here, we'll go ahead and get started. So we got this Goby3 course Git repo that'll be available in your virtual machine when you download that today in the homework. And within this directory, if I go into the source bin patterns folder, what I've got are these two, what I'm calling patterns. You could call them templates, but I'm avoiding that because there's a sort of term overload with C++ templates. And these pattern files are just a starting point for an application. And within each one of these, there's 3 files. And I would expect for most of the stuff you're going to write for this course, you'll end up copying these pattern directories, using those, and then building your code around them. And that's actually how I wrote the project code here because of that. It's a lot easier than writing it from scratch every time. But before I have you do that, I want to build these up from scratch because there'll be no magic copying around code here, at least without understanding what's there. So there are these 3 files: app.cpp, cmake.list.txt, and config.proto. This is the actual code for your application, the actual C++ code. And of course, there's no reason you couldn't have this in several headers and a couple CPPs if you want, but a lot of the stuff we're going to be writing here is short, so it can just live in one file. The second is the CMake list, which is just how CMake, which is the build system we're using, knows how to build our application. And the third is this config.proto, which is a protobuf message that defines the valid configuration for our application. So let's get started here by building up this, essentially what you're seeing in this pattern directory, but from scratch. And what I'm going to do is I'm just going to create an application and call it my app for lack of anything better. So if I make a directory of my app, I'm going to create a new blank file called app.cpp. And So all the Goby applications inherit from a particular subclass. So if I I mentioned in the lecture, there's a single thread application, and that corresponds to the actual class Goby3 single thread application. And then in the case of the multi-thread, we have the very similarly named class Goby3 multi-thread application. And I also want to put that these sort of the core files that I went through here, the app.cpp, config.proto, and cmake list. So if we're going to use the Goby's application support, we need to create a subclass of one of these two, single thread or multi-thread. And we'll use the single thread one because it's simpler, and you can explore the multi-thread one on your own, but it's a very simple extension of the same ideas. So we want to use single thread application. We need to include the header that that's actually in, which is Goby3 application single thread.h. And then I can create a class that I'm going to call my app, for lack of a better name here. You know, this would be what you're actually building. So if you were building a GPS driver, this would be called GPS driver or something like that. So single thread and multi-thread application are template classes. They take a single template parameter, which right now I've just put in ... here for. And what that parameter is the configuration that your application can support. So this is going to be the parsed version of what's given to your application on the command line or in a configuration file. And how do we go from the command line configuration file to the application here is through this concept called a configurator, which is I talked about a bit in the slides, but I'll bring it up in here. It's just, you know, goes from the command line parameters to the config object. And the default configurator, as I mentioned as well in the lecture, is this protobuf configurator. So what you do is you define a config message in protocol buffers, and the protobuf configurator takes the fields that you put in there, and that says those are your valid command line syntax and your valid configuration syntax. And so in order to use the protobuf configurator, I need to define a file for it. So that's what the config.proto is for. So I can now create config.proto. And if you're not familiar with protocol buffers at all, I would recommend taking some time this afternoon, take a look over the documentation for it, get yourself a little familiar with it, because I'm going to assume some level of familiarity for the rest of the week. So it may make your life easier. And for those of you, are you looking into that? We're using a Proto 2 syntax, the sort of old version of it. There's no reason you couldn't use Proto 3 in Goby, with the exception of DCCL, which is based around Proto 2. So for consistency, though, I'm just going to use Proto 2 so that we have just one syntax for protobuf messages throughout the week. But if you go to writing your own code, keep in mind that if you prefer, you can use Proto 3. So I'm declaring a package name for my configuration, and a package is protobuf's generic terminology for what ends up becoming a namespace in C++. And then within that package, I'm creating a message. And I, as a convention, there's no reason you have to do this, have called the message the same name as the class, but within the config namespace. You could very reasonably also call this like my app config if you wanted to. It's a style preference. So at a minimum, we need to include this app block that I mentioned a minute ago, which includes things like the glog configuration and the time warp settings. So to do that, I need to import, which is protobuf's version of include, the app config proto. And then I need to add a field to my message called app. And it must be called app, and it must be of this type app config. So that's going to be something you're going to just copy paste if you're going to use the single thread or multi-thread wrapper classes. The other thing that we're almost always going to have in the single thread and multi-thread applications require it is the interprocess portal config. And this is as I mentioned a few minutes ago, how you communicate to the Goby3 and how it's configured which Goby3 you're going to communicate to. And I also, in order to include that field, I need to include the appropriate header into process config proto. So that at a minimum is all that you need in order to configure your process. Almost all the time you're going to have something else in here because you're going to want to be able to take stuff off the command line or the configuration file and use it in your application. So for this example, I'll say I need to read an integer value called value A off the command line. Not that exciting, but since this is so generic, I'll call it value A. And so anything you could have any amount of protobuf information here, and then you could then add it to your configuration file or to the command line. All right, so now that we have this configuration message, we can use the C++ version of it in the app.cpp as our template parameter. So I need to include the header for it, which is config.proto, turns into config.pv.h. Code doesn't know about it yet because I haven't compiled it, so that doesn't exist, but it will shortly. And then within this template parameter for the class, I just provide that config, which, looking back at the proto message, the package becomes a namespace, and my app is the name of that message, which becomes a class. So on the C++ side, it's config namespace my app class. Okay, so now that we got that, we also need to have a main function because you can't have a C++ binary without a main function. And so if you're going to end up using the Goby configurators and the Goby classes, the main function is very short. You're going to use Goby run, which is what actually runs the application, and it'll with a particular configurator. So as I mentioned, you have the protobuf configurator, which also has to be given the configuration object that it's going to configurate with. I don't think that's a word, but it will be now. And then you pass the command line parameters to the configurator, which then configurates them into this class and passes it to the application. So at a minimum, and this is generally most of the Goby apps will just have this very simple main function. And as I mentioned in one of the slides, you don't have to use these wrapper classes. You can just use the transporters and stuff directly, but it is a nice, easy way to get people started with a project. So if you're of the don't wrap the main function type of view set, you don't have to, but it is convenient. All right, so now in order to do anything with this, we need to build it. So that's the last of these three things is my CMake list.txt file. So we're going to create a CMake list.txt. And so this course is not about teaching CMake. And so this is the one thing I'm going to sort of just copy and paste into here, but I will at least rationalize what all of it does. So this is kind of the only line you're going to want to change. When you create an application, we're setting a CMake variable called app to the name that I want my application to be built. In other words, what I run on the command line. Then it's going to generate the configuration file into the C++ version of the protobuf, which creates this config.pv.h that we're going to use. It actually builds the binary, links it against some Goby libraries, and then the protobuf messages in this Goby3 course project. And the final thing is if exports the interfaces file, which we'll look at tomorrow, maybe Wednesday, some more. But this is the data that's used to drive those static analysis figures that I briefly showed in one of the slides today. And so for you can copy this whole thing and then just change the app name at the top, but it shouldn't be entirely magic, hopefully. So the only other thing before I can type build is going to be in the parent directory. It has to know, the CMake list has to know to include this new directory that I've added. So if I go up a level from my app and then open the CMake list that's in that directory already, I have to add my new subdirectory to that list, or else it won't get built. And this can be a common thing that you forget to do. So if your code doesn't even try to build, that's probably why it's missing that. So now that we've got all that in place, we're ready to build. at the top level directory of Goby3 course, I've got this build.sh script, which you can use. It's not magic. All it really does is run cmake and make, well, cmake -- build, which is usually make. It could also be Ninja if you wanted to, but it's just a helper script. You can use it, or you can just do cmake make, whatever you feel like. So we'll let that build, and it looks like it wanted to rebuild all my code in here, which is fine as well. So while that's building, we can kind of continue on filling out the app.cpp, because right now this doesn't do anything. It requires an empty class that we run. So, you know, it will build, but it won't do anything. So all of these Goby apps have the option to have a loop method. So this optional loop method is called at some regular interval. And you can use it or you don't need to use it. So we're going to use it just to show you, in this case, how you would use it. You would basically declare the loop method as an override. It's just a no arguments void function. And then, you know, I can do something inside of here if I want to, like write out a debug sentence that says this is called 10 times a second. And glog is actually in Goby glog, so I need a using declarative up here in order to use it as just glog. And this won't be called because the default is to not call loop ever. And if I want to call loop, I have to pass to the base class constructor the frequency at which I want loop to be called. So let's just say we want to call loop at 10 hertz. So there are two overloads. You can either use the double one, which assumes that what you put in there is hertz, or you can use the boost units ones and make it explicit. I encourage you to be explicit about units where you can, but if you find boost units becoming a real headache, don't use it. There's no right way to do it, any one thing. And so that should now construct this and at least call this loop method at 10 hertz, which does something now, I suppose, more than nothing. I'll let that build and get set up here. So at a minimum, you're going to need a Goby3 for everything, because it's what brokers the communication between all the processes on the interprocess layer. So I'll run with one without any arguments, which is default arguments. And that'll work fine as long as you only have one Goby3 running on a system. As soon as you want to run 2 or 3, you need to start defining the different names for them, and that's in the config for these two examples there. So for really quick and dirty prototyping, you can just run Goby3 without any command parameters, and then I can run my new process, which is Goby3 course my app. And this name comes from the fact that I called it Goby3 course my app in the CMake lists for it. So you can match those two. And if you want it to be called something else, change it here. And then I'm using little single v, which is equivalent to verbose output, so that I actually see my glog messages. If I run this, then I get to see my loop method is called at 10 hertz, and you can tell that pretty easily because the timestamp on each line ticks up by 1/10 of a second. All right, so that is almost your minimal working Goby application. I mean, it is minimal and it's working, so I suppose by definition, the one last thing I want to show you today is how to read the configuration value that you put in there. So as you might have remembered when we did a config.proto, we added this value A field. How do I actually get at that? So there's a class. Let me just come out of this for a second back here. So the configuration is accessible via this CFG. and the parent class. So in the case of single thread application, multi-thread application. So if I want to just write it out to the screen, I can do, my config value A is, and then CFG gives me the whole object, which is my app, dot value A in this case is how protobuf accesses its fields. And then, so if I were to rebuild that, we can pass something like value A to the command line like this, dash dash value A. So the protobuf configurator turns fields into command line flags, if you will, of the same name. And so if I run that, once this is done building, you'll see that, kill that so we don't lose it, but back to full screen here. Before it started spamming the loop stuff on me, it writes my config value A is 3. And not to belabor the point, but oops, if I change this to 5, it changes to 5. So you can pass any amount of configuration stuff to the command line. That way, if you ever want to know what your application actually accepts, instead of going back into the config.proto and always checking, you can just do dash dash help, which maps it onto the actual command line syntax. So here's your value A flag. And then here's your interprocess flag and app flag, the two default ones, which generally I won't specify a lot on the command line because it gets a bit messy too. And that's when it's better to use a configuration file. So the configuration file can be, the syntax for it can be printed out by doing example config from your app. And this spits out all of the configuration that you could possibly give to your application. So again, here's your app block, everything you could put in the app block down to here. And then the interprocess block, everything you conceivably put in the interprocess block. And then here's our little value A down here. So you could put the contents of this in a file and then pass the file name. And I've been using pv.cfg just for convention. It doesn't have to be called that. But you'll look at that as well some more in homework. So that's the end of today's lecture. What we built up here in the last part is going to be identical almost to what you see in the source bin patterns single thread directory here. And so, you can build it from scratch again each time, or you can copy this directory if it's easier. I'll leave you with that option. And so tomorrow we're going to look into COM stuff, get our hands on the inter-vehicle, inter-process, inter-thread publication subscription and everything related to that. So it'll be a pretty meaty code-based lecture. Everything will be in code here with no slides. Hope to not go too long, but it might be 5 to 10 minutes over. And be prepared for that. Or if you have a hard stop, you're welcome to watch the last bit in replay. So that, let me open up Slack here and see what went down while I was giving this lecture. And I'm going to ask you, if you don't mind, to ask your question in person. So if you're willing to unmute, I'll call on people. And if you're willing to unmute and then ask your question, it'd be great to see some faces. The first question I got here is from Jim. So Jim Pricey, do you want to ask your question?
Sure, Toby. I guess I have two questions. You can take them in any order. One is, I didn't see specifically, I did not see you list Riptide vehicles as a type of vehicle that had drivers pre-developed for it. You had Bluefin and an Ivor vehicle and stuff. Are there drivers available for Riptide vehicles? Is one question. Second question.
Well, let's deal with one at a time.
Okay.
So that question, no, there is no Riptide driver in Goby at this point in time, because I haven't used a Riptide vehicle myself directly at this point in time. It should be pretty easy to write one because they already have a Moose-based interface, I believe. but one does
Okay.
not exist in the open source project.
Okay. And it seems like, I guess another question sort of went back to it. I'm looking at how you describe this this LCM, I think it was LCM and Moose and ROS. And it almost seems like they're primarily communications interfaces themselves, as opposed to an entire autonomy system, which has a lot of intelligence, a lot of things it does on its own. Is that a misconception? The way you describe, you talked about them, then you said it, and Moose is this or Ross is this, and you were talking about how they handle communications. I assume there's a lot more to it than just that communications interface.
So with Moose itself, not really. It's that and a handful of there's some viewer stuff like a UMS, which is kind of allows you to see the variables that are published within Moose. But yeah, Paul is pretty much only supporting it as a comms layer. It's a publish subscribe architecture. They're not to be confused with Moose IVP, which is a separate project, whereas IVP, which we'll be looking at quite a bit Wednesday, is an autonomy system based around the interval programming mechanism, behavior-based autonomy that Mike Benjamin has. So I guess the clear thing to make is a distinction between Moose, which is the underlying middleware and is mostly, a comms architecture, and Moose IVP, the IVP part and all the stuff that brings, which is very much autonomy. As regards to ROS, there's tons of stuff in ROS. I mean, that it would be what I presented was a vast simplification of the simplest piece of ROS, which is the ROS comms layer. So there's tons of stuff, but much of it is developed specifically for non-marine specific applications. So there's a lot of so some stuff's useful, like various camera processing, image processing stuff, and things. Some of it we can and do make use of, but there's not yet really a serious community around autonomy for marine vehicles in ROS. And LCM is also basically just a comms layer at the core. All right, so what do we else? Any other questions here that we've got? Seems to be all I see on Slack. Does anyone else have a question that they want to give? Just jump on and give it, and hopefully we won't all jump on each other at once. If not, I can wrap up. And
yep, I do have a question. Is there a way for the notifier? You were talking about the notifier function that tells you when something that you have subscribed to has been published. Is there a way to kick off a process basically for that? Because I can imagine scenarios where you have an app that until there's something published, you either want that app idling and not burning up any cycles, or you want it not even running. And when something is published that it subscribes to, the app is kicked off.
So you mentioned notify as a Moose thing, I think.
You had when you were going through, I'm not sure, I was making my own notes trying to flip back and forth. You were going through a notification function that notified a process.
So notify is Moose's syntax for publish. It's just what they call publish. More generally, yes, you can certainly subscribe to something, and once you reach a subscription, you would then start actually doing. I mean, I'm getting, I don't want to get a little bit ahead of tomorrow's lecture. We actually look at the syntax of subscribing, but if for example I had some in Goby, and I can give you the same in Moose at some point if you want, but if I subscribe to some group here with the callback function, and as I said, I am jumping way ahead of stuff I haven't presented yet, but just to give you a sense. So if I have some message I want that's a start message, there's a variety of techniques in here that you could come up with. If you're using the single thread application, I think your main recourse is going to be to have, like, say, a member variable. It's not started yet, and then once I get this message, I set started to true, and then down here, either in loop or whatever, you can do your stuff, whatever that processing stuff ends up being. So So this is a case where you're waiting to get a message. In this case, it's just generically named message. It doesn't exist. I'm just prototyping code here. And as soon as I get that message, I kick off whatever I'm doing.
Right, but are you burning cycles going around that loop saying continually checking started?
Yeah, I mean, at 10 hertz. So if you don't want to do that, I would start going to the case where you would turn this into the multi-thread application. And then, well, let me just butcher this up a little bit and just
So so you use the word callback function. So can you have a thing that when a message arrives, there's a function that's called?
Yeah, that is this lambda, which again is what I'm going to show tomorrow. So this lambda is what's called when you subscribe, when you receive a message of the subscription.
So that could be the thing that starts your process. You don't have to have another thing. That could be, rather than saying started equals true, that could literally be the process you want to kick off.
So yes, the key careful thing is, and again, I'm getting ahead, is that, so these are all called in a single thread. So your loop is not going to be called if you're blocking any of the subscription callbacks. So if you're like, if this is going to take, I don't know, like 10 seconds to do or something like that, you either need to be aware that it's going to block all your other message handling, which may or may not be a problem depending on how much message you're getting in, and it's going to block your loop method. Or you can spawn a separate thread to actually do whatever your processing is. So if the only thing your application is doing is waiting for one message, doesn't have a loop and wants to do something, then that would be fine. You could do it in that callback. As long, of course, is that whoever's publishing these commands to do it isn't publishing them way faster than you can process them. So I think you should mostly, yeah. So this hopefully answers it. I would encourage you to ask it again at the end of the day tomorrow if it's still unclear, because at least then we will have built up this syntax, and it might make it a little bit more clear.
Okay. I think someone else just asked a question.
Yeah, Oscar, you wanna jump on and ask your question?
Yeah, sure. Earlier when you were talking about the interthread sort of protocol you use, you talked about the sleight of hand using memory pointers. Since you're using ZMQ already, is there any particular reason not to use the ZMQ in proc? That is, are there any particular benefits or sort of overhead that ZMQ might bring?
Yes, there are two reasons I don't use ZMQ in proc for the default implementation. Part of it is because I've been trying to, where there's a good solution in the standard library to do something, I just do that with the standard library. So there's nothing in the interthread implementation that requires an external dependency. So if you built your own interprocess layer based on, the new and exciting ZeroMQ of tomorrow, you wouldn't then be beholden to using ZeroMQ still to have a working interthread implementation. You would just need a valid C++ compiler. The other reason is because ZeroMQ improc is not actually, it requires you to serialize your message to a set of bytes and then send it between threads and then marshal it. So you actually have to have the cost of calling, say, protobuf.serialize and then protobuf.parse, which isn't huge, but is non-trivial for messages, say, that are like megabytes or even gigabytes in size. It would get really expensive to do that. So I'm not a huge fan of ZMQ improc, except I am actually using it as part of the implementation for the interprocess portal, which has two threads and they communicate via improc, but then they're just little tiny control messages. They're not big things. So yeah, there's two reasons. Those are the reasons.
Awesome, thanks.
All right, anyone else got any questions for me?
I have one last one, Toby.
Sure, go for it.
This isn't general, this is very specific. On my machine, we have put up one virtual machine. Will installing the second virtual machine interfere with that?
No.
Okay, so I can install the virtual machine for this course and not interfere with that one.
That's correct.
Okay.
If you're running them at the same time, you might have problems, but
I won't run
only run one or the other.
Got it. Okay,
mostly because of your RAM gets totally, so whatever you allocate to the virtual machine for RAM gets in use. So depending on how much RAM you've given both machines, you may run out if you run them both at once. But you can certainly have them both installed and then just run one, shut down the other, run the other, shut down. Cool. Well, then I'm gonna be on again at 1 to 3 today, and as well from 7 to 9. Oh, sorry, Madeline, do you have a question?
Just a quick question since Jim started the technical detail questions.
Sure, yeah, go for it.
I was wondering, I'm probably going to install natively and I'm working on that right now. And so my question was just, are you actually using the operating system that you put in the virtual machine or are you using another one?
I'm using 2004. Yeah, Ubuntu 2004.
Okay.
You can probably very easily, if you're just choosing to use whatever and you don't have a preference, use 2004. If you've already
Yeah, I'm
gotten
actually on Mac, so I was just
Okay.
curious. So
Yeah,
I'll work on that. And if
yeah.
I fail, I'll use the virtual machine.
Yeah, I mean, so I did put the instructions on HackMD for what I did to set up. There's a fair number of steps to getting everything configured. So just shoot me a Slack message or join one of the office hours if you need help with any of it, because the VM is intended to be really easy. You just launch it and it runs. Well, I guess what I think it's fairly easy to set up natively, but my idea was easy with everything I wrote may or may not be. So, if you run into trouble, let me know.
All right. Thank you so much.
Yeah, of course.
hi, quick question. I'm digging around trying to find the original link. Where do we go? Where do we go for this? You had some things like Goby3 source, etc. Or Goby3 course launch alpha, but where do we need to be to get that?
Okay, so let me post this right now in the homework here, the links. So I think the core place to look is going to be at the syllabus page, which I just posted. I posted it before in the announcements channel on Slack, and within that,
So it's in HackMD. Okay, got it.
I
got a
link if you'd
F404
like.
not found when I just clicked on that
Yeah,
link you just
because
posted.
I failed to type apparently. Try it now.
Okay.
And so more concretely, it'll become more clear once you get through Dave's homework, because that will include the Goby3 course repo checked out on the VM. And so I also posted the direct link to the homework 1 PDF in the homework day 1 overview homework channel, which.
And that has all the instructions for the links to where to get certain things.
Yes, it should. And if it doesn't, please let me know.
Okay, got it.
So once you have the VM checked out, that'll have Goby3 and the Goby3 course on it, and you can use it there, or you can, if you're going natively, you clone it onto your machine using git clone. I guess let me just, so that was a pretty clear question. I'll also put the link to the repo directly. So that's the direct link that I put in homework 1 for the Goby3 course Git repository. But if you're running on the VM, you can just download the VM; it'll be there. And the last thing I can relink is the setup for native if you want to. I want to view, and I'm going to caution that this is only if you're downloading the VM, you don't need to walk through those instructions. So don't do too more work than you need to. But this is setting up if you want to run it natively on your computer in 2004 or 1804. Should be fine for Ubuntu. Debian, the latest Debian should also work, but I haven't tested that.
Okay.
So like one more time, remind everyone that I'll be on Zoom meetings from 1 to 3 and 7 to 9 for office hours. I will post those Zoom links in the homework channel on Slack. So it'll be a different Zoom link than the lectures are. So just look in Slack for those if you want to jump on. I don't really have a great sense of how many people are going to join those. So if it becomes a lot, I'll ask you to coordinate your questions so that I can try to get through them all. If it's not, then it should be no problem. But so, just start by joining Zoom. And if we get a lot of people, I'll encourage you to ask your question on Slack first. Of course, if you ask your question on Slack, then I can also give a link to any of my answers that I give on HackMD, so that anyone else who has the same question can look at that first, try to streamline it a little bit. Otherwise, thanks everyone for attending. Hopefully I'll see a good number of you tomorrow morning as well. Okay, got some hands raised again. Madeline, you want to go ahead again?
Hi, will all the instructions that talk about today gonna be shown in the Chromebook 1 video?
Sorry, could you ask that again? I didn't quite catch what you asked.
I mean, all the instructions that talk about today gonna be shown in the homework 1 video. Okay, I see on YouTube that homework 1. I said.
I'm very sorry, I can't understand what you're asking me. Would you mind asking the question in Slack and I'll try to answer it? If you have
Yeah.
that.
So.
Are you asking about the stuff that he showed during the lecture being showed in the homework?
Yeah, why don't you ask the question in Slack and I'll try to get to it. I'm not entirely sure I understand what you're asking. Did you have another question, Madeline, or?
No, thank you. I just asked about it.
So
No, I didn't have another
whiteboard-
question. My hand was I had to unraise my hand apparently.
Okay, yeah,
Sorry.
no worries. Jim, did you have something more you're asking? Or you wanna-
I'm looking for the whiteboard again because I got to your GitLab. I got to your GitLab page, but I was I'm just going back to your whiteboard to try to look for the actual paths within GitLab to get various things, but I don't see it on the whiteboard.
We'll take that.
I'll dig through my.
We'll take that to Slack and I think we'll figure it out.
Got it.
Jim,
Okay.
Jim, I've posted the HackMD whiteboard to the the overview discussion day 1 channel. That was
Under Slack.
on Slack. Yeah, everything's
Yeah.
on
Okay.
Slack.
I'm having trouble remembering which is.
So Jim, just focus on Slack. That's the core thing. Everyone will revolve out from there. That's my goal.
Okay. Got it.
Um,
Okay. There we
So
go.
Slack is sort of, if it's not there, ask for it there and we'll put it there. And then everything else can spawn out from there. Because that's the persistent
Okay.
thing that I can
So
easily.
overview discussion. There's the whiteboard. Got it, Roger. Thank you. Okay. I mean, this just takes me actually just digging through some stuff. Just, prodding and trying to find out where stuff is.
Great.
So.
All right, well, I'm going to
Okay.
stop recording now. Thanks for everyone who joined today. Thanks for everyone who's listening to this in playback. And one last time, I will be online today if you have any questions at all. And I'll be on Zoom from 1 to 3 and 7 to 9 Eastern. Thanks
Thank you.
again and catch you later.